namely Nog Memorial Lecture. I request Director Professor Arvind to say a few words about Nog Memorial Lecture.
So the series of Nog lectures was instituted at IMSC in 2002 in the memory of late Professor Subhashish Nag. And it aims to promote research in mathematical sciences by inviting eminent mathematical scientists, one each year, to deliver a series of lectures, and one of which is a public lecture, like today's talk. And the speaker for today is Professor Chris Woodward from Rutgers. I request Professor Indranil to formally introduce him. Mike.
It's my pleasure to introduce today's speaker, Professor Christopher Woodward. He did PhD from MIT and he works in Rutgers University. He has made very important contributions in symplectic geometry, differential geometry, algebraic geometry, and mathematical physics. The title of his talk is Symplectic Geometry and Vortices.
I should use the mic. Okay.
Hear me okay? Does the mic work? No. It does work. It's okay? Okay. So thank you very much for the invitation. It's a great honor to deliver these Nog Memorial Lectures. I was told this is a public lecture, so I asked, what does a public lecture mean? They said, well, there might be some physicists and computer scientists here. Are there actually any physicists or computer scientists here? Okay, there are a few. Okay. So you're apparently the public. So my talk is symplectic geometry and vortices. So let me start off with just a simple example of some question that comes up in symplectic geometry. So let's let S2 be the unit sphere in R3. Is this the laser pointer here? So it should work maybe by, yeah, okay. So S2 and R3, and we have a collection of unit vectors. And the question is, I think of V1 up through Vn as, say, a polygonal path, like the figure on the left. And for randomly chosen vectors, this path is not going to close, and I can ask the question, how can I deform V1 up through Vn so that they form a closed polygon? I mean, of course, it's easy to write down a solution to this equation, but the point is, suppose I start with some particular collection of vectors. What's a good way of perturbing them so that they actually do give a solution? Well, the first way that you might think of doing that is to use what's called in mathematics the implicit function theorem. I mean, suppose that this sum is as small and n is actually odd, so that it turns out this means that the zero level set is a smooth submanifold of the product of two spheres. And then you can use the standard iteration techniques to find an exact solution. But what I want to talk about is, instead of a method of deforming so that you get a solution where you don't assume that the error is small. And that's a gradient flow method. So suppose I take the sum of these vectors, v1 up through vn, and I take their length. And, oops, I went back. So their length squared is a smooth function. Let's just divide by 2 just to make things easy. And then I can try and use the downward gradient flow of this norm squared to deform my v1 up through vn to a solution. And well, you can write down explicitly what this gradient flow is. The derivative is the dot product of the sum with the sum of the derivatives. And if you compute what the gradient flow is, that means that it's a gradient flow on each of the spheres in the product. But it's on each of the spheres, it's the the gradient flow of a height function where the height direction is given by the sum, v1 up through vn. So on each product, it looks like, here's a gradient flow of this height function, but this green arrow, that will be the direction of the mu, where the mu is the sum of these vectors. Any questions about the setup for this problem? So it's not in general true that downward gradient flows have limits, but this is one case where the limit exists by a technique of Lejazowitz. So let's call that limit psi infinity of v1 through vn. And this limit, of course, has to be a critical point of the function that you're taking the gradient flow of. And it's pretty easy to figure out what the gradient, what the critical points of this function are. One possibility is that all of the vi's lie in the same line as mu. So that's like a linear configuration. And what that means is that, this vector, if I go back into this picture on the previous slide, if the vector is at the top or the bottom, then it's fixed by the gradient flow of the height function, right? So the same thing over here. If all of these vectors point in the same direction as the sum, then these vectors are preserved by the gradient flow, and so that's a critical point. And the other way of getting a critical point is if you're actually at a global minimum, which is the zeros of this v1 plus vn. Okay. So the question we'd like to look at is which tuples of vectors actually flow to zeros? Does anyone want to guess? You're not allowed to guess if you've seen this problem before. It's true actually that a generic tuple will flow to a zero under the gradient flow, but there are non-generic solutions which flow to the other critical configurations, these linear configurations here. Okay, no guesses. So the answer has to do with what's called semi-stability. So if the suppose two of the vectors that you start out with are equal, because the flow on each factor is just this gradient flow of this direction mu, that means that they're going to stay equal for all time when you flow. So let's let m be the max number of vectors that are equal. If m is bigger than half the number of vectors, so something like down here. So this would be the case when m equals 4. Like 1, 2, 3, 4 of the vectors are equal and the other 3 are not equal. So m equals 4 in this example. Then you see in that case that you can't flow to a solution because the sum of these vectors is so big that you can't close it up with the other 3. I'm already here, distance 4 away from my starting point, so there isn't enough length in the remaining vectors to get back to the beginning of the path. Okay, and this turns out to be the complete answer. So either the max number of vectors that are equal is less than or equal to n over 2, that's called the semi-stable case, and you flow to 0, or m is bigger than half the number of the vectors, and then you flow to a linear critical point. And in fact, the critical point that you flow to would just be the one with these 4 vectors in one direction and then the other 3 going back. That would be the limit under the gradient flow of phi. Okay, so this is a special case of a result of Kirwan. Doyström added just a little bit to this, but it's basically Kirwan's result. And it's a result about symplectic manifolds. So let me remind what the definition is. So a symplectic manifold is a smooth manifold, and it's equipped with a closed, skew-symmetric, non-degenerate 2 form, omega. So that means on each tangent space, I have a pairing of tangent vectors, which gives me a real number. And an example, the standard example would just be the cotangent bundle of Rn. So R2n, in physics, a symplectic manifold would just be called phase space. And the 2 form is just the dqi's, which the dpi's. So qi's would be the components of the position, and pi would be the components of the momentum. So they're 2n total coordinates. So in the example that I started out with, we're interested in a product of spheres. So it's a formula due to Archimedes that if you take the standard form on the S2, just the standard area form, then you can write it as d theta wedge dz, where z is the height. So one consequence of this formula, and this is the way that he stated it, is that if I take the sphere and I take 2 blue lines for some heights, z1 and z2, then the area in between them, that's the red area, is 2 pi z2 minus z1. You know, in particular, the whole sphere has area 2 pi times 2, because that's the height of the sphere, so 4 pi. And so if I take a product of S2s and I take the standard area form on each factor, the symplectic form looks like this. It's d theta 1 wedge dz1 up to d theta n wedge dzn. This is in his book on the sphere and the cylinder. Okay, so we're interested in symplectic manifolds with symmetry. So let's take a connected Lie group. In a second, it'll be compact, but for the moment, just let's say it's just a Lie group, and suppose it acts on our symplectic manifold. Associated to that action are the generating vector fields. Like if the group is SO3 acting by rotation, you have rotation around X, rotation around Y, rotation around Z. What do we mean by a moment map? It's a G equivariant map from X to RK, so that if I stick in the generating vector fields into the symplectic form, then I just get the components of the moment map with derivatives. D phi I is omega d by d theta I, comma, whatever tangent vector you want to stick in there. So another way to say that is each generating vector field is the Hamiltonian flow of some component of the moment map. So what are some examples? Well, if I have my product of S2s, I can let G1, the circle group, act by rotation around the z-axis in each factor. So the generating vector field for that action is d by d theta 1 plus dot 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 d by d theta n. If I plug that into the symplectic form, then I use Archimedes. Archimedes says the moment map is z1 plus dot 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 zn, where zi is the height of in the ith factor. And now I can do the same thing for SO3. SO3 acts on S2 by rotation. The generators are the rotations not only around the z-axis now, but around the x and the y-axis. And so I just get this formula for the moment map. I just take a tuple of vectors, and I just take their sum. That's an element in R3. I think of that as the Lie algebra. Okay, so that was the moment map that I started with at the beginning. And now Kirwan's result is about, in general, what happens when you take the gradient flow of the norm square of a moment map. So it's called semi-stable point is called semi-stable if this gradient flow has limit in the zero level set of phi. And the quotient of the semi-stable locus by the complex group action, this is another definition of the Mumford quotient in algebraic geometry. So that's called x semi-stable. Those are the points that flow to zero. Then you mod up by the complex group action. And so this gradient flow of phi squared, I guess I should have put the square on the outside there. It defines a homomorphism with what's called the symplectic quotient, which is the reduced phase space. That's when you set all of the integrals of motion to zero, and then you mod up by the action of the, now I'm talking about a compact group. So this is something called the Kempf-Ness theorem in symplectic and algebraic geometry. Okay, so a simple example of this is complex projective space. So if I let G, this circle group, act on R2n by rotation in each factor, then the moment map is given by, well, it's only defined up to a constant. I can stick this 1 in front if I like. Then minus sum of p squared plus q squared for each factor divided by 2. So this would just be the sum of Hamiltonians for the harmonic oscillator in one dimension. I take the sum for all the factors. So if I take the symplectic quotient, I set that to 0. That means that I set the sum of the p squareds and q squareds to be 1. And then divide out by S1. So that's a 2n minus 1 dimensional sphere divided by the circle. So that's one definition of Cpn minus 1. But then there's the sort of more standard definition of Cpn minus 1 where you just take 0 away from Cn. So that would be the semi-stable locus and mod out by all non-zero complex scalars. So that would be the complex description. Any questions so far? Okay, so I want to talk about this point of view extended to infinite dimensions, which actually came before all of this stuff about Hamiltonian group actions. So in this setup, you now let C be a smooth projective curve over the complex numbers, and you look at holomorphic vector bundles over this curve. And one way of getting, so holomorphic vector bundle means that the transition maps are holomorphic. And one way of getting such holomorphic vector bundles is if you start out with the universal cover of the curve and you have a representation of the fundamental group of your curve, then you can take the universal cover quotient. So the universal cover times CR is just the trivial bundle, but now you mod out by the action of pi 1 given by this representation. And this bundle is flat, and so it has constant transition maps. So it's a particular kind of holomorphic vector bundle that you get this way. And Narasim and Seshadri looked at the question of which holomorphic bundles arise in this way. And the answer is that it's exactly those bundles which satisfy a semi-stability condition. In this case, the semi-stability condition says that if I integrate the trace of the curvature for any holomorphic subbundle divided by the rank, that should be less than or equal to the corresponding thing for the original bundle. No, actually, because I'm looking at flat bundles here, I'm automatically the integral of the trace of the curvature for those flat bundles will be 0. So in this case, the right-hand side is just 0, but it's convenient to define the semi-stability condition more generally. Oh, that's a typo. I'm sorry. Pi 1c goes to U of R. Thank you. Okay, so the sort of the analytic point of view on this story was introduced by Atiyah and Bott. So for their point of view was, let's suppose you fix just a complex vector bundle, not a holomorphic one. And I think of all holomorphic structures as the space of connections on E. So the way that works is that if I have a connection, then I have a splitting into the horizontal part and the vertical part. And I already have complex structures here and here. So this gives me once I have this splitting, then this gives me a complex structure on this whole thing. And conversely, it's not hard to show that if I have a complex structure and a Hermitian structure, then I get from that a connection. Okay, so I just forget about holomorphic structures, and I just think about connections. And I think about the space of connections as a symplectic manifold. So the symplectic structure is the tangent space to connections is space of one forms with values and endomorphisms of the bundle. So I take two of those, I wedge product, and then I integrate over the curve. And if I think of it that way, the action of gauge transformations on the space of connections has a moment map, and that moment map is given by the curvature. So for any connection, I get a two form with values in the endomorphism bundle called FA. And the components of that are in some sense the conserved quantities for the action of gauge transformations. So I want to talk about a generalization of this story where I have not only the connection, but I also have some sections. So this leads to what are called the vortex equations. So remember, a connection corresponds to a holomorphic structure. So it makes sense to say that I have holomorphic sections with respect to a connection. And then I can look at the action of gauge transformations on this data A together with the sections. And this turns out to also have a moment map. So I'll write down what the moment map is just in the case of tuples of sections like this. E is a rank R vector bundle. But the whole story really works much more generally for any group action with moment map. I'm just trying to make it less abstract by focusing on this one particular case. So this here really is the moment map for the action of UR on CRN. Okay. And a zero of this equation, a zero of the right-hand side, is called a vortex. But there's really a free parameter in this whole story, which is this is a two form with values and endomorphisms, and this is just an endomorphism. So in order to make the endomorphism a two form, I have to wedge it with some two form on the curve, and that's a choice in the theory, which you can play around with. And that choice is going to become very important later. Okay, and so then there are various generalizations of the Narasimhan-Seshadri theorem for vortices. And this is a very long story, and there are many, many papers about this. So for example, Bradlow wrote a paper about, say vortices on projective curves, and they correspond to line bundles with non-zero sections. Well, if you're looking at the curve is a projective line, then once you fix the degree of the line bundle, there's only one up to isomorphism. So really the freedom that you have in choosing this data once you fix the degree is just these sections, which are each section here is just a section of the degree D line bundle on P1, so it's a degree D polynomial in two variables, z and w. And each such polynomial has d plus 1 coefficients. So if I just put together all of the coefficients together, there are n times d plus 1 of them, and then I mod out by automorphisms of the bundle. That gives me a projective space, P of dimension n times d plus 1 minus 1. Okay, so a lot of these vortex moduli spaces, even though the equations are quite complicated, they have very simple descriptions. And that's an example of this. Okay, so the case that Sushmita Venugopalan and I have been working on lately is the case of vortices on C. So again, there's this choice of area form in the theory, and the area form that we're looking at is not one that comes by pulling back something from P1. It's really the standard Euclidean area form on C, dx wedge dy. And there's a lot, again, there's a series of papers about classifying such vortices. So for example, Taubes, in one of his first papers, studied the case of vortices on C with group just U1 and target C1. Yeah, the curve is not compact, right. And the area form has a singularity at infinity. If you would choose on C an area form which did extend over P1, then there would be no difference from what was done before.
So it's infinite volume, right?
Yeah, exactly. Yeah, infinite volume domain. So Jaffe's, so this appeared in a paper of Taubes and then in the book of Jaffe and Taubes on monopoles. And it's been used a number of times, for example, in Taubes' work comparing Seiberg-Witten and Gromov-Witten invariance on four manifolds. So along with Guangbo-Zhu, we generalized this to more general targets and more general groups. So I'll just give an example. If the group is UR and the target is CRN, then a tuple of a connection with sections A and U, 1 up through UN, is equivalent to a vortex if the rank is R generically. And what that means is that you can take, say, the leading order terms in U1 through UN, and this gives you a point in the Grassmannian, and then the fiber consists of the remaining lower order terms, CR and D. So again, these moduli spaces of vortices have very simple descriptions. The proof goes by using the heat flow for pairs, which is what Venugopalan did in her thesis. So this metric has infinite volume, but you can approximate it by larger and larger balls, where in each ball you make a part of that ball have some flat metric. And so then eventually you show by a method of exhaustion that anything with this semi-stability condition does in fact have a complex gauge equivalence with a vortex. In the general case, there's a more fancy way of phrasing this correspondence, which is to say that vortices on C with this infinite volume metric correspond to morphisms from P1 to the quotient stack, X mod GC, where you just enforce the semi-stability condition at infinity. But I don't have time to talk about stacks, even though some of the physicists probably like. I don't know, I'm at Rutgers, so stacks are very big in the physics department now. Okay, So instead of talking about the details of the proof, I want to talk about some of the motivation, which comes from Gromov-Witten theory. So in Gromov-Witten theory, you define the Gromov-Witten invariance as integrals over Konsevich's stable map space. So the way this works is, suppose that Y is some smooth complex projective variety, and then you have some moduli space of maps from a curve C to Y together with some marking Z1 up through Zn. And you fix the numerical invariance associated to this problem, like the genus and the homology class of the map. And now you say this has a nice compactification of what are called stable maps. So this allows degeneration of the curve in such a way that there are no infinitesimal automorphisms of the combined data consisting of the marked curve with the map. But one big problem with this theory is that this moduli space of stable maps is very complicated, even for the simplest case when the target is just a projective space. So what can happen is if I take a bunch of, say, genus 0 stable maps, I can just, as long as their images intersect, I can take, glue the domains together and get a more complicated stable map. So for example, in Pn-1, I just have lines, which are stable maps of degree 1. And I can patch those together to nodal curves to get some stable map whose image looks like this. So there'll be very complicated nodal degeneration. On the other hand, the moduli space of vortices, even though the equation is much more complicated, is very simple. We already saw that the corresponding moduli space in this case was Bradlow's moduli space, which is just a projective space. And that projective space is already compact. It doesn't need to be compactified. The difference here is that, see, a map to projective space is given by a tuple of polynomials. But in the stable map compactification, you're never allowing the polynomials to have common zeros. Right? They always have to map to projective space. Whereas in this vortex compactification, you are allowing them to have common zeros. And that means that the compactification is much simpler. Okay, so what's the relationship between the vortices and the stable maps? Well, I said before you have this free parameter, which is the area form on the domain. And if you just let that area form go to infinity, then what you see is that in the equation here, that forces this term to go to 0, right? This term becomes much more important than this term. And this term is just the moment map equation for the action. So you force the curve to map into the 0 level set for the moment map, and that map means it maps to the symplectic or Mumford quotient. This was an observation of Gaio and Solomon, and so there's now a more refined version of that statement, which says that the limit of any sequence of vortices with bounded energy is a collection of stable maps together with a collection of vortices on C. So the idea is that in this limit, you might have blow up of some of these sections, but whenever you blow up, you do a rescaling procedure, and this so that the blow up goes away, and then in the limit, you'll see that you have these vortices as well as the stable map. So what that means is that Gromov-Witten invariants of the quotient, like projective space, are related to the vortex invariance by some map which incorporates the C vortices. So this map we started calling the quantum Kirwan map, because if you set it up properly, it really gives you a map from the equivariant quantum cohomology of x to the quantum cohomology of the quotient. And what this means is that properties of Gromov-Witten invariance can be proved by first proving the corresponding property of vortex invariance and then taking this adiabatic limit. And especially the opposite limit of this vortex equation is especially simple. So if I look at this equation again, and now I take this thing to 0, if I take this to be 0, then that means that the curvature has to vanish. And at least if you're in genus 0, then there are no non-trivial flat connections. So that means in the opposite limit, you actually get a stable map to x. And those can be quite easy to understand. For example, if x is a vector space, then there are no stable maps at all, because it's affine. There are no homologically non-trivial spheres in any vector space. So this limit really becomes very easy. So it's this fact that you can play around with this parameter in the vortex equation, which means you can get applications out of this stuff. So I want to talk about some of the applications and to Gromov-Witten theory that we're trying to work out. So these are all in general open questions, and they're open questions just because it's so hard to work with these stable map spaces. So one application is it's in general not known or very difficult to compute Gromov-Witten invariance of non-abelian quotients like Grassmannians or flag varieties or quiver varieties. But it's much easier to compute the corresponding quotients by the maximal torus. So, for example, the Grassmannian is a quotient of a vector space by UR, and the corresponding quotient by the maximal torus is just a product of projective spaces. So that makes things much easier. Another thing which is not known is how do you understand the Gromov-Witten theory of a complete intersection in terms of something in the ambient space? And that's known how to do that by work of Giventhal and others in the case when the complete intersection is corresponding to some positive line bundles, but if you lose the positivity condition, then people don't really understand this. So this is another thing you can do by sort of going to vortices and going to this opposite limit, because in this opposite limit, the positivity problem goes away. A third problem is how to understand K-theoretic Gromov-Witten invariance. So in K-theoretic Gromov-Witten invariance, instead of just integrating over the moduli space of stable maps, you integrate in K-theory. So that means you take Euler characteristics of sheaves instead of integrals of cohomology classes. So there's been a lot of interest in this recently because of some work of Nekrasov-Shadashvili and Akunkov-Malik, who related this to quantum integrable systems. And the K-theory versions are supposed to be really much more natural than the cohomology versions. But it's really difficult to compute the K-theoretic Gromov-Witten invariance of anything. Even the case of K-theory of projective space or Grassmannians was not known until very recently. Okay, so this is not the only strategy to look at these questions. So Chokan, Fontaine, Kim, Giventhal, Halpern, Leistner, et cetera, have other papers about this. In particular, Giventhal and Chokan, Fontaine, and Kim tend to use localization techniques for some sort of residual torus action. But the strategy that we're pursuing is really answer the corresponding questions about vortices first, and then use this limiting procedure to get the corresponding answer about the Gromov-Witten invariance. Okay, so I'll stop there. Thank you.
Well, I have some question. You see, I didn't understand what you said. Looks like this from vortices you are getting some information on the about the Gromov-Witten invariant.
Yes.
Or is it one way or it goes both ways? I mean, does it?
It could go both ways. If you could compute the Gromov-Witten invariance, then yeah, you could also compute things about the vortex invariance. So in most cases, the symplectic quotient is more complicated than the original variety. But that's not always the case. I mean, you could have symplectic quotient be very easy, although the original variety is very complicated. And then it might be interesting to try and go the other way, to try and use the stable map invariance to tell you something about vortex invariance. Yeah, but there's always this indeterminacy. Let me see, where is, so there's always this map which relates the two kinds of invariances, this quantum Kirwan map. And you always have to compute this in order to get some relationship. And this is the thing which is sort of very hard to compute. Because it itself is defined as a count of some integral over some moduli space, which may be just as difficult as a stable map space. So that's why sometimes you can compute what this map is and sometimes you can't. So an example would be for toric varieties. We can compute what this map is, essentially. But for the Grassmannian. But in general, we don't have a good tool to compute that. Oh, okay. Previous.
This thing Z1, etc., Zn, are there any condition on the maps U on those points?
So the way that the Gromov-Witten invariance would be defined would be that you would pull back cohomology classes under the evaluation maps at those points and integrate them over the moduli space of stable maps. But if your cohomology classes are represented by cycles and your moduli space is sufficiently nice, then you could just think of it as the number of maps with these data sending the mark points to those cycles. So then it really is just the number of maps satisfying constraints at the mark points given by the cycles that you've chosen. But that's not true in general. I mean, as soon as you get outside of the projective space type examples, then you need more sophisticated definition.
So that means those will be taken to some fixed points in Y, is it? Meaning the fixed endpoints in Y.
Not necessarily fixed points, but you would constrain those Z's to map to some cycles, like some subvarieties. Yeah. Like in the first papers, like by Kontsevich and so on, he really looked at the example where you have point constraints. You really fix the ZIs to map to some fixed points that you choose. But that's not true in general. I mean, you could just have some.
Cycle that you have fixed.
Yeah, that's right. Yeah.
Well, if there are no other questions, let's thank the speaker again.